FAMOSE, a ReAct approach to automated feature discovery. Kiefberger 1 Dina Lee 17 Static 1 Uning How 1 Bola 1 Abstract feature engineering remains a critical yet challenging bottleneck in machine learning, particularly for tabular data, as identifying optimal features from an exponentially large feature space traditionally demands substantial domain expertise. To address this challenge, we introduce FAMOSE, feature augmentation and optimal selection, and a novel framework that leverages the ReAct paradigm to autonomously explore, generate, and refine features while integrating feaure selection and evaluation tools within an agent architecture. To our knowledge, FAMOSE represents the first application of an agentic ReAct framework to automated feature engineering, especially for both regression and classification tests. Extensive experiments demonstrate that FAMOSE is at or near the state of the art on classification tests, especially tests with more than 10k instances, where ROCAUC increases 0.23% on average and achieves the state of the art for regression tests by reducing automacy by 2.0% on average, while remaining more robust to errors than other algorithms. We hypothesize that FAMOSE strong performance is because ReAct allows the LLM context window to record via iterative feature discovery and evaluation steps what features did or did not work. This is similar to a few-shot prompt and guides the LLM to invent better, more innovative features. Our work offers evidence that AI agents are remarkably effective in solving problems that require highly inventive solutions, such as feature engineering. 1. Introduction. Despite the simplicity of tabular models, their performance is often difficult to optimize. Namely, while carefully engineered features are often the most important component to 1. Amazon.com Inc. 410 Terav and Seattle, WAP 98,109, United States. Correspondence to Kiefberger, Coburg at Amazon.com. Preprint, February 20, 2026. Figure 1. Types of AutoML. In traditional AutoML, feature engineering would include feature discovery such as within OpenFE, Deng et al. 2023, or iterative feature modification such as the method of Perdamathu et al. Perdamathu and Sikwa 2009. Although LLM methods such as COF often excel at feature generation, iterative feature modification has not been explored as often before now. FAMOSE offers a way to learn through trial and error which features work and which ones do not until a better feature is developed. Model performance Eden 2016. T. Schultz et al. 2024. Their optimization remains a difficult and time-consuming bottleneck. This is because identifying those valuable features is extremely difficult. The space of potential new features, transformations, or combinations of existing attributes is enormous, and only a small fraction will ultimately prove useful. As a result, designing features has traditionally relied on human intuition and domain knowledge, and it continues to consume a significant portion of a data scientist's effort. Bengio et al. 2013. To reduce the manual burden, the variety of automated feature engineering techniques have been proposed, whether algorithmic methods such as OpenFE Zhang et al. 2023, or LLM-based methods such as COF Hallman et al. 2023. However, these methods struggle due to the combined networkly large space of features to evaluate. Zhang et al. 2023, Horn et al. 2019. While LLM-based methods may offer a route to search the space more efficiently, these methods do not iteratively improve on their prior features by learning from their mistakes. This can be illustrated in Fig 1 R 2.1Z641B1 theta.LG 9 2026. FAMOSE, a ReAct approach to automated feature discovery. To address these limitations, we introduce FAMOSE, feature augmentation and optimal selection and a framework that utilizes ReAct agents for autonomous feature engineering. The agent iteratively proposes, evaluates, and refines features rather than generating a static list in a single pass. FAMOSE therefore simulates a data scientist who iteratively hypothesizes tests and refines features to improve predictions inspired by the reasoning and acting paradigm. The agent can reason about the task, execute code, and adapt its strategy based on validation performance, enabling a feedback-driven search process similar to how human practitioners experiment with features. Unlike one-shot or template-based approaches, the agent can directly interact with the dataset to compute statistics, inspect distributions, and test hypo says about feature utility. As a result, feature proposals are grounded in the actual data rather than relying solely on prior knowledge. The iterative loop also allows the agent to detect and correct invalid or unhelpful features, reducing hallucinations and improving robustness. By learning from empirical outcomes, the agent can more effectively navigate the feature space and focus on transformations that are in for meta and context. Moreover, during the ReAct process, the LLM explains the reason it chose this feature, improving feature interpretability. At the end of each round, the best feature that improves model performance if one is found is saved. At the next round, we restart the ReAct agent to create yet more features. Each new feature's performance is then evaluated conditional on the original features and all the saved features from prior rounds. Once performance stops increasing at the feature discovery step, FAMOSE then applies a minimal redundancy maximal relevance MRMR feature selection step and pen 2005 to produce a compact final feature set. This final step contrasts with prior work that used the LLM itself for feature selection. Hall, Men et al. 2023. We expect that algorithms might select features more accurately than LLMs, so MRMR is chosen as a reasonable feature selection tool. The entire process is fully automated and generalizes across data classification and regression with diverse dataset sizes and feature dimensionalities. In summary, our contributions are as follows. ReAct-based feature discovery. We propose a ReAct agent framework to autonomously generate, evaluate, and refine features through iterative interaction with the data. Comprehensive benchmarking. We evaluate our method on a diverse suite of classification and benchmark datasets and check model robustness via evaluating its performance on multiple tabular models as well as an alternative LLM. State-of-the-art performance and robustness. The proposed method matches or exceeds state-of-the-art performance across classification and regression tests and can create features in datasets where some AutoML methods fail. This is especially true for large classification datasets, for example, more than 10k instances where FAMOSE performance is substantially higher than competing methods. Feature interpretability through reasoning. We leverage LLM-based reasoning to provide human interpretable explanations for why generated features are useful. Overall, this algorithm offers a simple, scalable, and robust method for feature discovery. Moreover, while LLMs have been understood as general power machines, Merchant Donnie et al. 2023, our work offers evidence that AI agents can be remarkably effective at solving problems that need highly innovative solutions despite the limitations of LLMs at creating diverse outputs. John et al. 2025. 2. Related work. Automated feature engineering has long been studied to improve prediction performance, where carefully engineered features have been shown to outperform gains from model selection or hyperparameter tuning alone. Eden 2016. Early work focused on pre-processing data, namely creating compact or latent representations of data, including Prince Cell component analysis. PCA, Abbey and Williams 2010. In PCA, a new set of orthogonal features are created that represent the largest amount of variance in the data. PCA can be used to reduce the feature space into a subset of distinct features, although this only creates features that are linear functions of the original features. A substantial body of work, however, has investigated combinatorial and search-based feature engineering. This includes AutoFeed Horn et al. 2019, Diverju et al. 2022, and OpenFE Zhang et al. 2023, which each create a set of new features based on transformations and operations on older features and then prune the resulting feature set. Other examples include Explore KitKats et al. 2016 and Deep Feature Synthesis Counter and VRMocha. Many 2015, also CF Heated 2016, Margijan et al. 2017, Davis and Fu 2016, Margijan et al. 2017, which generate candidate features by enumerating transformations over existing features, then follow a heuristic or model-based evaluation for feature selection. While these approaches can produce interpretable features, they often struggle to scale efficiently with memory or time because the search space increases enormously with the number of features in the original dataset. Moreover, because the transformation rules are predefined, these methods may miss domain specific. 2. FAMOSE, a ReAct approach to automated feature discovery, or multi-step feature constructions that fall outside their templates. An example of multi-step feature construction, however, includes Paramafu and Sequoia 2009, which it creatively creates new features based on features it already created. But this idea has not been as carefully explored in AutoML literature. Recent literature has begun to address the limitations of traditional AutoML with LLMs. Namely, LLMs have recently been utilized for feature generation or transformation. Hallman et al. 2023, Deng et al. 2024, Hand et al. 2024, Nem et al. 2024, E et al. 2025, Padiankar et al. 2025, which expands on prior work utilizing LLMs for tabular data understanding. Feng et al. 2024, Wing et al. 2023, Din et al. 2022, Il et al. 2024. A state-of-the-art LLM-based feature engineering tool is Hallman et al. 2023, which uses an LLM to suggest new features based on dataset metadata and test descriptions. In contrast, Feed LLM Han et al. 2024 treats feature generation as an optimization problem guided by LLM proposals. Related efforts explore evaluating or benchmarking LLM-generated features. Jin et al. 2024, Ort et al. 2024, or Good in feature construction using model-based reasoning. Nam et al. 2024. These methods demonstrate that LLMs can propose creative and context-aware features that go beyond simple transformations. However, most existing LLM-based approaches follow a one-shot or template-driven workflow. Features are generated once, evaluated externally, and not iteratively refined by the LLM itself. As a result, the model cannot learn from feedback, correct and valid feature defining tones, or adapt its strategy based on empirical performance. Once features are generated, a large body of work has developed. Feature selection tools Chandrasekhar and Sang 2014. Many heuristics have been explored. CF Dan et al. 2023, Horn et al. 2019, Atz et al. 2016, Kudra and Virmach many 2015, etc., which we will not have space to explore in depth. However, one widely used selection method is minimum redundancy, maximum relevance, and RMR Din and Peng 2005. This method selects a subset of features based on minimizing redundancy, for example, minimizing correlations between features while maximizing their relevance. For example, finding features highly correlated with a target variable. Other methods of feature selection include LLMs. Hallman et al. 2023. Although we expect algorithmic feature selection is more accurate than LLM-based methods, a comprehensive comparison between these methods have not been explored. In contrast to prior approaches, our work's most substantial contribution is that FAMOSE uses a ReAct framework. Yao et al. 2022, in which the LLM iteratively proposes, evaluates, and refines features based on model feedback and data-driven analysis by integrating reasoning, acting, and validation within a closed loop. This approach aims to add algorithm 1 FAMOSE 1 input dataset D equals X Y base model M 2 output selected engineered feature set F 3 split data K equals 5-fold stratified to classification 4 for each fold 5 split training data into train and validation 6 initialize feature set F left arrow 7 define EZ the error of a model in validation data 8 evaluate baseline score on validation set 9 4 equals 1 to 20 do 10 for step equals 1 to 10 do 11 agent proposes a feature F using metadata and tool feedback 12 validate feature code 13 if validation fails 14 agent creates new code 15 end if 16 if 1 minus EXF F slash EXF 0.01 then 17 continue 18 end if 19 end for finds dot TEXFF is maximized 20 if EXFF 0 then 21 F left arrow FF 22 end if 23 end for 24 apply MRMR to select final features F 25 train using F and evaluate on test fold 26 end for address the scalability, robustness, and adaptability limitations observed in prior automated feature engineering methods. In addition, our work conditions the performance on new features with the performance of the model with all prior picked features, allowing us to find features that add more signal to our prediction tasks than all previous features. 5. We utilize a traditional algorithm for feature selection, MRMR Ding and Peng 2005 rather than an LLM Hall and et al. 2023, which we believe allows for fast and accurate feature selection. Free methodology. In this section, we describe the FAMOSE methodology for feature generation, the datasets used to evaluate FAMOSE, the experimental setup, and the baseline algorithms. 3.1 FAMOSE. We outline FAMOSE in algorithm 1 with an example of FAMOSE in Fig. 2. FAMOSE at its core is Smollett, Jen Sriracha et al. 2025 with additional tool and a post-processing evaluation algorithm to ensure that the best free FAMOSE, a ReAct approach to automated feature discovery. Features are selected. Small Agent is an open-source AI agent that can think, act, and observe, but can hallucinate without appropriate tools. We removed its core tools except for the Python code compiler and created a metadata generator tool that allows the agent to determine data file column names, features, and whether the column values represent numeric, count, data time, or categorical data. This allows the agent to better understand features without manually incorporating those details into the prompt. We also provided it with a feature evaluation tool in which code generated by an LLM is used to generate a feature column. The model perfects ROZDUZ or RMC and held out data containing the candidate feature, the original features, and all of the best features chosen so far is compared against a model without the candidate feature. If a change in performance is positive, the feature improves model performance. We negate RMC so that a positive change always represents a better model. The tool is highly robust with the help of error correction and regex to extract all the feature names in the feature code. If the feature names include hallucinated features or if the code cannot run, then the tool forces the agent to correct its mistakes, including the replacement of hallucinated features with correct ones. Data provided to the feature generation code also has the target variable removed to avoid data leakage. We provide the following prompt for the agent. See details of prompt and agent output in the appendix. We first set FI role data scientist and the relevant files and feature descriptions. See example feature descriptions in appendix. Tables S3 and S3. We then ask the agent to 1. Use all of these insights to create a large set of new features. It can use any mathematical operations or transforms. 2. Explain why this feature is useful. 3. Check the performance of each feature with a feature evaluation tool. 4. Set a goal to improve feature performance by 1% and do not stop until this is achieved. 5. Return the best feature. The agent will then autonomously use the file metadata tool, create Python code, and evaluate features with appropriate tools. If the agent discovers that a feature did not improve performance by at least 1%, it will iteratively improve on and evaluate new features for up to 10 agent sets until it is satisfied. Top right of Fig. 2. At this point, the agent will stop and a feature evaluator algorithm will then evaluate all the features created by the agent and pick the best feature that improves model performance if any are found. This post-agent step addresses situations in which Figure 2. An illustration of FAMOSE applied to the bound scale past Sealer 1976. FAMOSE first invents features and observes their performance, in this case using the difference in arm weights to see whether a scale is balanced tilting right or tilting left. If performance is insufficient, FAMOSE then thinks about how to create better features, ultimately discovering the feature moment that exactly predicts whether a scale is balanced. Because the performance cannot be improved further in this task, the feature discovery step eventually stops. The feature selection set then selects this feature using MRMR Ding and Peng 2005 and removes the 4 extraneous features in the test dataset W1, W2, L1, and L2. Thus, instead of an error-prone model with 4 features, we discover a perfect predictor with only 1 feature. The LLM hallucinates model performance in order to satisfy the 1% model performance improvement goal. Finally, the agent repeats all these steps for up to 20 rounds or until the performance has not improved after 6 rounds. This stops the algorithm early to save time. Adding features, however, could contribute to overfitting a model, so we use MRMR bot 2003 to select the best features as shown in the bot. Tom right of Fig 2. This contrasts with other sort of feature engineering methods Hallman et al. 2023, Piers et al. 2025, in which the LLM itself decides what features to remove. We specifically use use 5-fold cross-validation within the training dataset to find the optimal number of features to select based on ROC, AUC, or RMC, then apply an RMR to the training dataset to select the specific features. 3.2. Data. We evaluate our approach on a diverse selection of public tabular datasets, including 20 classification tests and 7 regression tests, spanning over 3 orders of magnitude in size. All datasets are outlined in Appendix Table S2. These dataset tests cover binary and multi-class classification, e.g., income prediction, medical diagnosis, game outcomes, as well as regression problems, for example, health prices, insurance costs. We specifically chose these datasets from a prior paper, Biancar et al. 2025, but added additional tests from Table that contain over 10K instances to ensure that ROC, AUC differences were more statistically significant. Most datasets analyzed are commonly used as benchmarks, and a smaller subset of these have been used in many prior papers. Horn et al. 2019, Allman et al. 2023, Biancar et al. 2025, and et al. 2024. We borrow feature descriptions and 4. FAMOSE, a ReAct approach to automated feature discovery. Task descriptions, i.e. what the model aims to predict from Biancar et al. 2025. Although we correct feature names, 4 vehicles Hebert, 1987, Bound Scale Siegler, 1976, and Sinancy Lim, 1999, whose feature names were miswritten in the GitHub code for Biancar et al. 2025. For example, column names were lowercase when they should be capitalized, or contain spaces when they should contain underscores. For datasets not mentioned in app, Biancar et al. 2025, and for bank marketing Morrow et al. 2011, which also contained errors in feature descriptions, we instead use feature descriptions from each dataset's respective webpage, e.g. Kettle. All dataset links are referenced in Appendix Table S2. Table S1 summarizes the key characteristics of the datasets, including the number of instances, number of features for classification test class, and balance fraction of data in the smallest class, and for regression tests, the target variable variance. We also list in Table S2 a brief description of each prediction task. For training/validation and testing, we use scikit-learn SK-folds if regression or stri, 5K-fold if classification with K equals 5, and use a random seed of 42. Pedregosa et al. 2011. We further stratify training data into training and validation using K equals 5, where validation is used to select FAMOSE features, or to determine the number of features to select for MRMR. Test folds are only used for the final performance evaluation. 3.3. LLMs and resources. For LLM-based feature engineering, we use AWS Bedrock, Sonnet 3.5 v2 LLM, and DeepSeek-R1, as they have reasonable speed, performance, and cost, while the main text describes results using Sonnet 3.5 v2. We also report DeepSeek-R1 in the appendix and find it predates similar quality features. Following prior workup, Biancar et al. 2025. We fixate LLM's temperature to beat 0.8. Fine-tuning such hyperparameters will be important. Research in the future. Analysis was made with AWS Sage. Nader ML.R6i.32x large and ML.M7i.48x large instances for most data, but we use a GPU instance, ML.G5.48x large, to train AutoV1 Derton et al. 2020 cdef/https://instances.vantage.sh/ for a summary of instance specifications. We do not expect variations in instances will have a significant impact on model performance because the resources needed to run LLM inference are unknown and could affect LLM speed. We do not compare algorithm inference times, especially the speed of LLM methods against classical methods. We would expect that if classical methods were given the same resources, perhaps tens of GPUs as an LLM like Sonnet 3.5 v2, we should expect far different speeds. That said, because we have limited time to analyze data, we do not include performance for classical algorithms that created pairs or take more than 10 hours for all 5 folds to finish with an ML.M7i.48x large instance. LLM-based methods, meanwhile, typically finish a few minutes and therefore do not have such restrictions. Even the longest time for FAMOSE to complete all 5 folds of a task is roughly 6 hours COFAT, which contains 580K instances and 55 features. 3.4. Prediction models. We compare different feature engineering approaches using XGBoost, as this is a common high-quality tabular model baseline. While XGBoost performance could vary based on hyperparameters, we use 12 parameters and set the seed to 42 for consistency. We also apply the XGBoost derived features to random forest Brennan, 2ThumE1, and AutoV1 in order to determine the robustness of these features across models. Other models can also be tested on FAMOSE. We believe the models we choose represent examples of state-of-the-art tabular models. Boosted trees XGBoost, ensembles of trees random forest, and weighted ensembles of deep learning boosted and founded on models AutoV1. 3.5. Feature engineering baselines. We compare our methods against 2 classical methods, AutoFeed Horn et al. 2019 and OpenFE et al. 2023, as well as Soda LLM-based methods Koff Hall and et al. 2023 and Feed LLM Han et al. 2024. For LLM-based methods, we replace a call to the OpenAI API with a call to AWS Bedrock, a change of just a few lines in order to easily switch between various candidate LLMs we aim to use, but all other code was kept the same. We do not report comparisons against another recent baseline LLM FE Biancar et al. 2025, as their results are hard to validate. Metadata was miswritten in their code, as mentioned above, and details of model implementations, including model hyperparameters, are missing. Finally, they report results such as normalized RMSE, but do not say how they normalized RMSE, for example, normalized by the mean or range within the test set or training set, etc., making the results they report unreproducible. Smaller issues include the category preprocessing step in their code converts categories into float numbers so that the model would interpret the categories dog, cat, and car as 0, 1, 2, where 2 is greater than 0. We believe this is not an adequate way to represent non-cardinal categorical variables due to challenges in producing their results and the incorrect preprocessing step they use on data. We cannot be certain we replicated their work, so we leave out this model that said our best guess at reproducing their results shows significantly worse performance than our method or COF. In some datasets, we find column names contain unusual characters, e.g., or, which would confuse classic 5. FAMOSE, a ReAct approach to automated feature discovery. Cal methods AutoFeed or OpenFE. AutoFeed and OpenFE read and write for the formatted files, which cannot natively parse those characters. For the classical feature engineering methods, we replace column names for with left right bracket and with less greater than, despite results reported in a Biancar et al. 2025. The simple change in the column names dramatically improved the robustness of each of the classical methods, and the only errors were due to out-of-memory errors. For example, creating and then selecting among millions of features would require TBs of memory, or more rarely, out-of-fan errors. 4. Results. In Table 2, we show classified performance, the mean ROC, AUC after applying FAMOSE, and 4 competing SOTA methods, AutoFeed Horn et al. 2019 and OpenFE Jane et al. 2023, both classical methods, and Feed LLM Han et al. 2024 and Koff Hallman et al. 2023, both LLM-based methods. For any multi-class tasks such as bound scale, we calculate an unweighted average of 1 versus 1 ROC AUC. We find that FAMOSE is statistically and significantly different from the pseudo-math odds, and consistently find AutoFeed and OpenFE fail to handle particularly complex datasets or data with more than 10K rows. This is because the number of features these models analyze scale greatly with the number of columns, which in turn creates, e.g., GBs of memory for moderately large datasets. Unfortunately, this means classical math odds fail for many realistic datasets. Feed LLM meanwhile fails or performs poorly for different reasons, often due to issues including creating roles for multiple classes, or because the LLM output will end without completing the task. Koff and FAMOSE meanwhile can work across all tasks. While we find OpenFE is strongest for tasks with fewer instances, FAMOSE pulls away for tasks with more than 10K instances with a mean improvement of 0.23%. We chose 10K as a a reasonable compromise between size and number of tests 7 out of 21. We compare features developed by Koff and FAMOSE in the appendix, where we find that FAMOSE creates many more diverse functions. FAMOSE also performs strongly for regression tests, where it is better than the competing methods. AutoFi and OpenFE LLM methods we evaluated do not create features for regression tests. Namely, we find a 2.0% reduction in RMSE on average, as shown in Table 1 Wilcoxon sign. Rank test p-value equals 5.7 between FAMOSE and the baseline. Importantly, FAMOSE again performs well in both small and large tests, while classical methods often fail. To evaluate larger tests, success rate is 90%. Interest in Glide. OpenFE performs especially poorly for the bike test, although we are unsure as of yet why its performance is consistently worse across all folds. In addition, however, to model performance, we see in appendix 2 that FAMOSE output achieves human interpretability. For example, when applying FAMOSE to the balance scale test, we see, much like 2, that the agent can test and decipher moment difference is the only feature needed to capture whether a scale is balanced or tilts. We apply an alternative LLM, DTCAR1 Guo et al. 2025 to FAMOSE and decipher performance is similar. See tables S5 and S6 in the appendix. The model performance is therefore robust to the type of LLM chosen. We also see the features evaluated for XGBoost models were well in Random Forest Brandon 2001 and AutoBlue1 models. See tables S7 and S8 in the appendix. The features FAMOSE deciphers appear to work well across a variety of models. We can also test whether FAMOSE can be ablated to a simpler model. Appendix tables S10 and S9. We find, for example, that removing the goal in our prompt improve performance by at least 1% can sometimes lead to lower performance. We believe this is because the agent decides to stop the results early without working hard to create ever better features. We similarly find, as expected, that feature selection alone is insufficient to boost model performance, thus motivating feature engineering. For example, balance scale achieves ROC AUC of 1.0 once an LLM feature related to torque is discovered, but feature selection would never discover this feature. Similarly, that model performance is reduced when we do not select features, which is needed to simplify an otherwise complex model. In conclusion, we find one FAMOSE ReAct framework can create sort of features in both classification and regression tests, especially for tests with more than 10k instances. 2, creating a goal for FAMOSE improve performance by at least 1% can further improve model performance, and 3, FAMOSE-based features derived from one model can improve the performance of other models. 5, discussion. Our proposed ReAct framework. FAMOSE is a novel way to create sort of model performance for classification tests, especially large classification tests as well as regression tests. Moreover, the features engineered by FAMOSE improve the performance of both weaker e.g. Random Forest and stronger e.g. AutoBlue1 models. If FAMOSE is applied to a fast and simple model, our results suggest that an end user could be reasonably confident that FAMOSE engineered features can also improve the performance of a more powerful, slower, or costlier model, thereby saving time or money in the process. 6. FAMOSE, a ReAct approach to automated feature discovery. Test baseline OpenFE AutoFeed FAMOSE like 40.3 plus or minus 1.03 92.09 plus or minus 6.35 41.47 plus or minus 1.01 40.05 plus or minus 0.99 crab 2.32 plus or minus 0.13 2.26 plus or minus 0.15 2.34 plus or minus 0.08 cybersecurity attacks 0.82 plus or minus 0.0 0.82 plus or minus 0.0 housing 409.58 plus or minus 10.54 432.87 plus or minus 10.22 403.96 plus or minus 9.61 408.56 plus or minus 26.34 insurance 192.89 plus or minus 13.91 190.23 plus or minus 11.18 187.6 plus or minus 12.48 191.64 plus or minus 11.16 forest fires 92.7 plus or minus 5.34 88.52 plus or minus 5.91 93.49 plus or minus 5.42 79.49 plus or minus 5.87 one quality 0.64 plus or minus 0.02 0.75 plus or minus 0.03 0.62 plus or minus 0.02 0.64 plus or minus 0.01% reduction up arrow 0.0% 20.7% 0.3% 2.0% percent test analyzed up arrow 100% 86% 71% 100% table 1.RMSE comparison of FAMOSE to SOTA feature engineering algorithms across 5 folds. OpenFE Zhang et al. 2023 and AutoFeed Horn et al. 2019. The percent reduction is the mean percent reduction of RMSE across all folds and tests. This is calculated by replacing any algorithms that could not run with a baseline performance. Bold indicates best model. Test baseline OpenFE AutoFeed feed LLM Koff FAMOSE. Balance scale 0.914 plus or minus 0.01 0.999 plus or minus 0.001 0.977 plus or minus 0.0251 1.0 plus or minus 0.0 0.965 plus or minus 0.022 1.0 plus or minus 0.0 blood 0.698 plus or minus 0.03 0.681 plus or minus 0.048 0.677 plus or minus 0.033 0.426 plus or minus 0.063 0.697 plus or minus 0.03 0.704 plus or minus 0.027 rest W 0.989 plus or minus 0.007 0.993 plus or minus 0.004 0.993 plus or minus 0.006 0.994 plus or minus 0.004 0.99 plus or minus 0.01 0.989 plus or minus 0.008 core 0.999 plus or minus 0.01 plus or minus 0.01 plus or minus 0.00.86 plus or minus 0.019 0.999 plus or minus 0.00.997 plus or minus 0.003 CMC 0.704 plus or minus 0.019 0.693 plus or minus 0.013 0.683 plus or minus 0.019 0.709 plus or minus 0.031 0.7 plus or minus 0.02 0.696 plus or minus 0.023 communities 0.866 plus or minus 0.8 0.808 plus or minus 0.011 0.864 plus or minus 0.861 plus or minus 0.7 Critigy 0.771 plus or minus 0.036 0.772 plus or minus 0.023 0.775 plus or minus 0.026 0.711 plus or minus 0.035 0.783 plus or minus 0.024 0.757 plus or minus 0.04 Euclidus 0.835 plus or minus 0.01 0.907 plus or minus 0.09 0.903 plus or minus 0.08 0.83 plus or minus 0.014 0.836 plus or minus 0.021 Hort 0.919 plus or minus 0.023 0.919 plus or minus 0.022 0.914 plus or minus 0.026 0.92 plus or minus 0.021 0.917 plus or minus 0.023 0.903 plus or minus 0.027 Myocardial 0.688 plus or minus 0.082 0.686 plus or minus 0.093 0.592 plus or minus 0.054 0.679 plus or minus 0.09 0.679 plus or minus minus 0.05, PC1 0.822 plus or minus 0.05 0.795 plus or minus 0.104 0.82 plus or minus 0.049 0.701 plus or minus 0.055 0.834 plus or minus 0.033 0.832 plus or minus 0.064 detect 0.999 plus or minus 0.21 plus or minus 0.999 plus or minus 0.2 0.999 plus or minus 0.21 plus or minus 0.1 table 0.929 plus or minus 0.007 0.952 plus or minus 0.007 0.951 plus or minus 0.003 0.792 plus or minus 0.008 0.93 plus or minus 0.008 0.918 plus or minus 0.021 small test percent improvement up arrow 0.0% 1.04% 0.92% 7.6% 0.47% 0.36% adult 0.929 plus or minus 0.02 0.896 plus or minus 0.2 0.887 plus or minus 0.929 plus or minus 0.2 0.929 plus or minus 0.2 bank fraud base 0.886 plus or minus 0.04 0.837 plus or minus 0.05 0.718 plus or minus 0.7 plus or minus 0.3 0.886 plus or minus 0.3 bank marketing 0.934 plus or minus 0.05 0.738 plus or minus 0.02 0.933 plus or minus 0.04 0.928 plus or minus 0.013 call touch 0.99 plus or minus 0.994 plus or minus 0.743 plus or minus 0.003 0.99 plus or minus 0.989 plus or minus 0.01 diabetes 0.705 plus or minus 0.4 0.673 plus or minus 0.75 plus or minus 0.5 plus or minus 0.3 gym just 0.974 plus or minus 0.01 0.999 plus or minus 0.718 plus or minus 0.04 0.974 plus or minus 0.01 0.994 plus or minus 0.06 large test percent improvement up arrow 0.0% 1.77% 0.018% 15.9% 0.008% 0.229% overall improvement up arrow 0.0% 0.15% 0.62% 10.2% is risk 0.32% 0.32% test analyzed up arrow 100% 89% 58% 84% 100% table 2.ROCAUC comparison of FAMOSE to SOTA feature engineering algorithms across fivefold auto feed Korn et al 2019 OpenFE Jing et al 2023 feed LLM Han et al 2024 and Koff Hallman et al 2023 algorithms that could not run due to errors are indicated by the percent improvement is the mean percent increase in ROCAUC across folds and tests. This is calculated by replacing any algorithms that could not run with a baseline performance. Bold indicates best model. In contrast to prior methods, FAMOSE effectively simulates a data scientist by iteratively hypothesizing, testing, and refining features to improve predictions. Moreover, FAMOSE self-ReActs code to robustly develop new features for a rich variety of datasets. We hypothesize FAMOSE ability to create useful features is due to the LLM context window, recording the features that did and did not improve model performance, which is akin to few-shot learning, allowing new features invented by an agent to improve on the mistakes of features the agent invented in previous steps. Overall, our results hint at ways that AI agents can be general problem solvers in situations that require highly inventive solutions such as feature engineering. More specifically, with the help of post-processing checking to reduce hallucinations and the right tools and prompts, other agents can be able to similarly develop trustworthy error-free outputs in highly inventive tests. 5.1 Limitations. There are several limitations associated with FAMOSE. First, the ReAct framework can be expensive due to the number of tokens needed for agentic chain flow reasoning. In addition, FAMOSE appears to perform more poorly on cheaper and smaller LLMs based on our initial exploration of FAMOSE with Llama 3.1-AP. Third, the benefit of FAMOSE depends on the background knowledge available to the LLM. For example, the LLM will perform better on a common test than a test very different from the text it was trained on. Our AG framework might help in these scenarios by inserting more bespoke background. 7. FAMOSE, a ReAct approach to automated feature discovery. Knowledge of the test to the LLM prior to the feature generation step. Finally, FAMOSE will need to be modified to create features for multi-label classification, but we expect such modifications would be minor. 6. Conclusion. We introduced FAMOSE, a novel ReAct-based algorithm to automate feature engineering for tabular machine learning tests. This approach reduces reliance on deep domain expertise, speeds up responses to emerging patterns, and lays the groundwork to automate the end-to-end machine learning lifecycle. FAMOSE utilizes agents to create features and evaluates the features again after the agent finishes it. Test to control for LLM hallucinations. Finally, it selects a subset of features with MRMR to optimize model performance. Using these features, we found SOTA performance improvement across classification and regression tests, especially for large classification tests. These features were found to work well across various models and came with explanations written by the agent's LLM, which helps humans better understand these features in contrast to many non-LLM methods. Impact statement. This paper presents work whose goal is to advance the field of machine learning. There are many potential societal consequences of our work, none which we feel must be specifically highlighted here. References: Abdi H. and Williams Hill. J. Principal component analysis. Wiley interdisciplinary reviews. Computational statistics. 24:4 33 4 5 9 2 10. Biancar and Chai P. and Reddy C. K. LLM feat. Automated feature engineering for tabular data with LLMs as evolutionary optimizers. RZIF preprint. RZIF colon 3.4434 Editor and Venugable U. Cybersecurity text https://www.kettle.com/dataset/teamencrypt. OSAT cybersecurity text/data 2024. Ahadi. Tic-tac-toe endgame. UCI machine learning. Repository 1991. https://doid.org/10.244322c5 felon 688j Earngender 245k. Do healthcare insurance expenses https://www.kettle.com/dataset/earngender or 245/health insurance expenses/ 2023. Better be and Coadi R. Adult. UCA machine learning repository 1996. Doid https://doid.org/10.244322c5xw20. Bendio Y. Kervil and Vincent P. Representation. Learning. Review and new perspectives. IETD Transet. Jones on pattern analysis and machine intelligence 35.8. 198 128 2013. Blotter J. Covered it. UCI machine learning repository 1998. Doid https://doid.org/10.244322c50k5n. Bohank M. Car evaluation. UCI machine learning repos. Iterate 1988. Doid https://doid.org/10.244322c5jp48. Board test. Nori H. Rodriguez B. Maship B. and Caruana R. Elephants never forget. Memorization and learning. Tabular data in large language models. RZIF preprint. RZIF colon 2454.06209 2024. Raymond Hill. Random Forest. Machine learning 45.1 532 2001. Bullock B. Euclid. Disso conservation. https://www.kettle.com/dataset/euclid. S 1996. CDC. Diabetes health indicators. Dataset https://www.kettle.com/dataset/elixirval/type test indicators dataset 2015 Chandrasekhar Dia Insight in F a survey on feature selection methods. Computers and electrical engineering Inc 41:1628-2014 Listen 0045 def 7906 https://doi.org/10.1016/j.compile10.2013110124 URL https://www.sciencedirect.com/sign e/articles/45/SCME4579061 year commemorative issue Cortes PM Moise a data mining approach to predict forest fires using meteorological data in proceedings of the 13th 2007 pp 512-523 Demaris Portugal 2007 Cortes P Serta 8 Omega F Autos T and Rise J modeling wine preferences by data mining from physico-chemical properties in decision support systems Ball U47 pp 547-553 LCR 2009 Davis J and Fui automated feature engineering for HTTP tunnel detection. Computers and security 59:166-185 2016 Ding C and Peng H minimum redundancy feature C legend from microarray gene expression data. Journal of Bioinformatics and Computational Biology 302:185 205 2005 A FAMOSE, a ReAct approach to automated feature discovery. Din T, Sang Y, Ding R, Lin Z, Geo M, Rajvat, S, Zone JY, Hatayopulos, D and Lead K, Liv, language interface fine-tuning for non-language Chime learning test. Advances in neural information processing systems 35:11,763 11,784 2022 Ericsson and Mueller J, Turkov T, Ding H, Larry P, I, M and Smollett A, Audibly 1 tabular, robust and accurate AutoML for structured data. RZ for print, RZ:2 3.06505 2 Funny TH, byte sharing dataset 2023 URL https://www.kettle.com/data 6,194,875 Feng X, Su W, 10F, A, Jing J, Hu Z, Tai Y, J, Niklich S, Sokolin CD, 3 of Singambu, S and Files C, large language models LLMs on tabular data, prediction, generation and understanding. A survey. Transactions on machine learning research 2024 URL https://www.amazon.science/p applications/large language models LLM S on tabular data prediction generate ion and understanding survey Fedisoriano heart failure prediction dataset https://www.kettle.com/dataset/Fedisorian /heart failure prediction 2021 for AJ Expedia travel dataset https://www.kettle.com/dataset/checkup of ready/x I travel dataset/data 2022 Gotch H G. Scientific method in practice Cambridge University Press 2003 Golovin S Shulman V Rossif T Chesterna P Mikalina S Orlova Y. and V. Netzi The myocardial infarction complications USAC Machine Learning Repository 2020 by https://joy.org/10.24432/C53P5M Guo D and D Ding H Sung J Ding R Su R 2 Q Bias Wing P by XL DTCAR1 incentivizing reasoning capability in LLMS via reinforcement learning.RZ for print RZ:2091.12948 2025 Guvenir H Car P Muters Lu H and Quinlan R Hithia UC Machine Learning Repository 1997 doi https://joy.org/10.24432/C5BS32 Hannes Yun J Erkas Owen Fisher T large language models can automatically engineer features for few-shot tabular learning.RZ for print RZ:24/4.09491 2024 PT Juan S Do Y Long Q Kyle Z U M Fu Y Q Y. And ZO M Fast accelerating rain forced feature transformation via advanced exploration strategies.RZ for print RZ:2023.20394 2025 Heaton J empirical analysis of feature engineering for predictive modeling in Southeast Con 2016 pp 16 2016 doi m.1109 2.2.20 Hoffman H Stella German credit data USAC Machine Learning Repository 1994 doi https://joy.org/10.24432/C5 and C77 Hallman N M double.R S and header F large language models for automated data science introducing COF4 context-aware automated feature engineering in OA Noman T Globes and A Cinco K Hart M and Levine S Eds Advances in Neural Information Processing Systems Volume 36 pp 44,753 Current Associates Inc 2023 URL https://proceeding s.nerds.cc/paperfiles/paper/2023/5.8c2dnf4c35cdb764 eb9 e9d0 act 599 7 paper conference.pdf horndef hack R and reader M the AutoV Python library for automated feature engineering and selection in Joint European Conference on Machine Learning and Knowledge Discovery in Databases pp 111-120 Springer 2019 Ilan J P Wing C Berger S Ramos T W V Rich N Brown D Marshall D and Gao J data analysis in the era of generative AI.RZ for print RZ:24/5.18475 2024 Jesus S Humble J L T Cruz A Saro P Ribeiro R and et al turning the tables by Symbol S dynamic tabular datasets for ML evaluation 2022 URL https://www.kettle.com/dataset/sgp/bank account fraud dataset 10 URITS 2022 John L Chai Y Liam Liu M Fuck R DZA N Tsec of Y Sephem Abelek and Choi Y artificial hivemind the open-ended homogeneity of language models and beyond.RZ for print RZ:2510.22954 2025 Kedar J M and Viomatani K deep features and this towards automating data science endeavors. 2015 IEEE International Conference on Data Science and Advanced Analytics DSOP pp 110 2015 URL https://api.semanticsco.org/corpus ID 206,610,380 Hetz T Shin E C R and Song D X Explore Kit Auto Mag Feature Generation and Selection. 2016 IEEE 16 International Conference on Data Mining Lectum pp 979 984 2015 URL https://api.semantics.org/corpus ID :4 4 68 932 mine FAMOSE, a ReAct approach to automated feature discovery. LMTS, contraceptive method choice. USAC Machine Learning Repository 1999. https://joy.org/10.24432/C59W2D. Merchant 9 S. ZF. Florence P. Victor B. Reese D. Arenas M. T. Rauke. Sega D. N. A. Larg. Language models as general pattern machines. RZ. Preprint RZ:23.7.04721 2023. Laura S. Moreno R. and Cortez P. Using data mining for bank direct marketing and application of the CRISP-DM methodology in proceedings of the European Simulation and Modeling Conference 8th and 2011 pp 117-121 2011 Mem J. Kim K. O. S. Tech J. Kim J. and Shin J. Optimized feature generation for tabular data via LLMS with Decision tree reasoning database is in neural information processing systems 37:92003 to 92,300 E 2024. Nargesian F. Samulovitz H. Tirana U. Khalil E. B. and Tirada D. S. Learning Feature Engineering for Classification. AICAI Volume 17 pp. 2029 2035 2018. Pace R. K. and Barry R. Sparse Spatial Autoregressions. Statistics and Probability Letters 33:291 297 1997. Header goes at F. Verbox G. Grumford A. Mitchell V. Therian B. Brisselville. Blondel M. Predenhofer P. Weissar. Duberg V. Vendivus J. Cassis A. Kerr. Dado D. Roger M. Parrott M. and Duchesne E. Scikit-learn. Machine Learning in Python. Journal of Machine Learning Research. 2018 25 2018 30 2011. Pierre A. S. Valkyrie A. Habati P. Lozano L. C. N. Elwood A. An LLM-based approach for insight generation. In data analysis. RZIF for print. RZIF 28 and 3.11664 225. Pedamathu S. N. Sigua R. T. Iterative feature construct John for improving inductive learning algorithms. Expert systems with applications. 362:354 Redmond M. Communities in crime. USEC. Machine Learning Repository 2002. Doi. https://doi.org/10.2444327C53X. Roger A. Moral A. V. D. T. Wolf L. V. W. and Cap. Ismati E. Small agents. Small library to build great agentic systems. https://github.com/hidden. Face and Small agents 2025. Sayed Shirabad. J. and Menzies T. The Chromis Repository of Software Engineering Databases. https://www.ml.org/search app equals data and sort equals runs and ID equals 1068 and status equals active 2005. Sidu G. S. Grab Aid for Edition 2021. URL https://www.kettle.com/DDC/2,834,512.cbert J. Vehicle recognition using rule-based methods. Turing Institute Research Memorandum Term 87-018 1987. Siegler R. Alan Sale. UCI Machine Learning Repository 1976. Doi. https://doi.org/10.24432/C5 488X. T-shots of A. Martin S. L. Edk Bart T. and Stucknishnet H. A data-centric perspective on evaluating machine learning models for tabular data. RZIF for print. RZIF:24 7.02112 2024. Vemran J. and Invest J. K. Endgame analysis of Dushu Kai.opimo.org/search app equals data and ID equals 409 98 2014. Wengar. Wang Z and Sun J. Unipredict. Large language models are universal tabular classifiers. RZIF for print. RZIF:2310.03266 2023. Wahlberg W. Breast cancer was an original. UCF Machine Learning Repository 1990. Boy. https://doi.org/10.24432/C5HV4D. Yao S. Zhao J. UD. Du and Jeffern I. Nersaman K. R. and Kao Y. ReAct. Synergizing reasoning and acting in language models. In the 11th International Conference on Learning Representations 2022. AISE. Blood Transfusion Service Center. UCF Machine Learning Repository 2008. Boy. https://doi.org/10.2444322/C5GS39. Zhang T. Tang Z. A. Fan Z. Luo H. Liu F. Liu Q. Kao W. and J. and L. Openfeet. Automated Feature Generator. John with expert level performance. International Con. Ference on Machine Learning PP. 41,880 41,901. PMLR 2023. Thang Y. IN. Gang Q. Jang W. Whip DN. Wangcam. Elfdom. Evaluating large language mod. Else-generated features for tabular prediction. Improv. Seedings of the 33rd ACDEM International Conference on Information and Knowledge Management. SICM 24. PP. 5,425,424. New York. NY. USA 2024. Subject John for computing machinery. ISBN 92009-8bit-4 Doi. 10.14. Sayuri meets sin 73.3679153. URL https://doi.org/10.14. Sayuri meets sin 73.3679153. Joji. Suzy. UNC and Wan Y. Different Tibla Automated Feature Engineering. International Conference on Automated Machine Learning PP. 17.1. PMLR 2022. 10. FAMOSE, a ReAct approach to automated feature discovery. A. Appendix. Adapt 1. Full LLM prompt. The full prompt is below. Prompt. You are a data analyst expert with full knowledge of data analysis methods. You have been given the following file. File name. This is a CSV file useful to enter the question. S. Determine if an individual has diabetes, no diabetes, pre-diabetes, or diabetes. In addition, we have the following descriptions of each column. Dictate of each feature and description. Your tests are the following. Only perform one task within your code. Do not write the code for multiple tests at once. Test 1. Use all of these insights to create a large set of new features. You can use any mathematical operations or transforms. Do not use any black box models such as random forest, XGBoost, light GBM, etc. and do not use the diabetes feature in your newly generated features because that trivially improves model performance. Test 2. Explain why this feature should help answer the question. S. Determine if an individual has diabetes, no diabetes, pre-diabetes, or diabetes. Test 3. Check the performance of each feature by creating a dict of the form code::ser code of function new feature df. That will run on a data frame returns the feature as a pandas series, stating this dict object with pandas to pickle as a file named new feature text status at 0 and p.random.random100,000.pkl and running the feature performance evaluator tool. Test 4. High performance values are better if the feature performance evaluator score is over 0.01. Move to the next test. Otherwise, create more features and try again. Test 5. Save the best performing feature. Use pandas to pickle to save a dict object of the form code::ser code of function new feature df that when run on a data frame returns the feature as a pandas series. Save as a file name new feature datasets random number.pkl where you create a random integer with number. Do not use pickle.dump to save this dict object because you will get an error. 2. Example implementation. We show an example of how this algorithm works on one exemplar test. Balance scale. This test aims to predict whether a scale slides to the left, right, or is balanced, making it a 3-class classify problem. We are given 4 features: left arm length, left arm weight, right arm length, and right arm weight. In theory, we only need one feature. The difference in torque left arm length times left arm weight minus right arm length times right arm weight. The 4 features, when fed into pseudo methods, gives us ROZDUC of 0.8 for random forest table S7 or 0.91 for XGBoost table 2. Interestingly, the performance is 0.995 for AutoW1, demonstrating it is a very good, although not perfect, tabular model. FAMOSE output is as follows, given a prompt like what is seen above. 11. FAMOSE, a ReAct approach to automated feature discovery. But I'll help solve these tests step by step. Thought. For test 1, I need to create meaningful features for predicting a balance scale direction. Since this is a physics problem, I can use the principles of moments and leverage. The key insight is that the product of wave and distance gives the moment/torque on each side, and comparing these will determine which way the scale tips. Code. Import pandas as PD. Import numpy as NT. Hash read the data. df equals pd.read c/v.data/balance scale train 3.c/c. Hash create features based on physics principles. Def create features df. Hash calculate moments torque for each side. Left moment equals df left weight asterisk df left distance. Right moment equals df right weight asterisk df right distance. Hash calculate moment differences and ratios. Moment difference equals left moment right moment. Moment ratio equals left moment/right moment. Hash calculate total weights and distances. Total weight weight equals df left weight plus df right weight. Total distance equals df left distance plus df right distance. Hash calculate squared terms. Left moment squared equals left moment asterisk 2. Right moment squared equals right moment asterisk 2. Hash calculate log transformation setting 1 to avoid log 0. Log moment ratio equals np dot log 1p moment ratio. Hash create feature dictionary. Features equals moment difference, moment ratio, total weight, total distance, left moment squared, right moment squared, log moment ratio, return features 12. FAMOSE, a ReAct approach to automated feature discovery. Output colon hash create the features. New features equals create features df. Print created features. List new features dot keys. Flash code. Observation. Created features. Moment difference. Moment ratio. Total weight. Total distance. Left moment squared. Right moment squared. Log moment ratio. Thought. For test 2, I'll explain why these features should help predict the bound scale direction. Code. Explanation equals. The created feature should help predict the bound scale direction for the following reasons. 1 moment difference left moment right moment. If positive, the scale tips left. If negative, the scale tips right. If 0, the scale is balanced. This is directly based on a fifth principle of torque. 2 moment ratio left moment slash right moment. If 1, scale tips left. If 1, scale tips right. If equals 1, scale is balanced. This gives a relative measure of the imbalance. 3, total weight and total distance. These provide context about the overall scale of the problem. 4, squared moment. Captures nonlinear relationships and emphasizes larger differences. 5, log moment ratio. Transforms the ratio to handle skewed distributions better. Print explanation slash code 13. FAMOSE, a ReAct approach to automated feature discovery. Output colon observation. Printed explanation of feature importance and physics principles. Thought. For test 3, I'll test the performance of one of our most promising features, the moment difference, as it directly captures the physical principle determining the scale's direction. Code. Import pickle. Hash create the feature function for moment difference. Feature code equals def new feature df. Return df left weight asterisk df left distance df right weight asterisk df right distance. Hash create dictionary with a feature code. Feature dict equals code. Feature code. Hash save the feature dictionary using pandas. Random number equals np dot random dot random 100,000. Fan name equals f new feature bound scale 0 random number dot pkl. pd dot typical feature dict. Fan name. Hash evaluate the feature performance. Performance equals feature performance evaluator. Fan name. Print f feature performance sort. Performance slash code. Observation. Feature performance sort 0.815. Thought. For test 4, since our feature performance evaluator score 0.815 is well above 0.01, we can proceed to test 5. Code. Hash create the final feature dictionary with our best performing feature. Final feature code equals def new feature df. Return df left weight asterisk df left distance df right weight asterisk df right distance. Final feature dict equals code. Final feature code. Hash save with pandas to pickle using a random number. Random number equals np dot random dot random 100,000. Final fan name equals f new feature bound scale 0 random number dot pkl. pd dot to pickle final feature dict. Final fan name. Final answer f successfully completed all tests. Final feature save is final fan name with performance score 0.815 slash code. After this output, it prints the following observation. 14. FAMOSE, a ReAct approach to automated feature discovery. Observations created features. Moment difference, moment ratio, total weight, total distance, left moment squared, right moment squared, log moment ratio. The created feature should help predict the bound scale direction for the following reasons. 1 moment difference left moment right moment. If positive, the scale tips left. If negative, the scale tips right. If 0, the scale is balanced. This is directly based on the physics principle of torque. 2 moment ratio left moment slash right moment. If 1, scale tips left. If 1, scale tips right. If equals 1, scale is balanced. This gives a relative measure of the imbalance. 3, total weight and total distance. These provide context about the overall scale of the problem. 4, squared moments. Captures nonlinear relationships and emphasizes larger differences. 5, log moment ratio. Transforms the ratio to handle skewed distributions better. Feature performance score 0.09026. Last output from code snippet. Successfully completed all tests. Final feature saved as new feature bound scale 0338885.pkl with performance score 0.815. We notice that the LLM hallucinates with a statement performance score of 0.815. Hence why all observations are checked. Post facto where we confirm the true oral CDUC performance improvement of 0.09026 within a validation dataset separated from the test dataset. This represents a change in oral efficiency from 0.91 to 1.0 within that dataset. We then use MRMR to optimize the number of features needed, which turns out to exactly the above feature. The final model is simplified to become a single feature model with perfect prediction. For context, other methods, even with comparable accuracy, will often have more features. 15. FAMOSE, a ReAct approach to automated feature discovery. Test cache data points, hash features, imbalance target variance. Adult 48,842 15.0.24. Rahithna 452 280.0. Bound sale 625 50.08. Bank fraud base 1,032.0.01. Bank marketing 45,211 17.0.12. Blood 748 50.24. Breast W 699 10.0.34. Communities 1994 130.33. Credit G 1021 0.3. Diabetes 253,680 22.0.02. Car 1,728 70.04. Cough 581,012 55 0.0. DNC 1,473 10.23. Eucalyptus 736 20.14. Heart 918 12.45. Jumbo chest 44,800 7.1. Myvardil 686 92.22. PC 1109 22.07. Tic tac toe 958 10.35. Vigil 846 19.24. Crab 3,893 9. 3.2. Bike 17,379 13. 179.7. Forest fires 517 13. 80.2. Housing 20,640 10. 1,024.5. Insurance 1,338 7. 386.2. Wine 6,497 13. 0.9. Cybersecurity attacks 40,025. 0.8. Table S1. Data specifics. Number of data points. Number of features. Data imbalance if a classification test for target variance if a regression test. 16. FAMOSE, a ReAct approach to automated feature discovery. Test type test prediction test. Classification adult better and co-heavy. 1996 earned more than $50 than per year. Yes, no. Arrhythmia Gouverneur et al. 1997 presence of cardiac arrhythmia 16 classes. Bound scale Siegler. 1976 bounce direction. Left, right, or bounce. Breast W. Wahlberg. 1990 breast mass malignant M or benign B. Blood 2008 blood donation occurred. Yes, no. Carbohack. 1988 car acceptability rating 4 classes. Diabetes CDC. 2015 diabetes status. None pre-diabetes. Diabetes. CNC limb. 1999 contraceptive method choice 3 classes. Communities Redmond. 2002 violent crime rate. Low, medium, or high. Cough up bladder. 1998 forest cover kite 7 classes. Credit G Hoffman. 1994 credit approved. Yes, no. Eucalyptus Bullock. 1996 utility classification. Heart Fedezuyano. 2021 heart disease present. Yes, no. Jungle chest Amran and Vis. 2014 winner of Jungle chest and game. Myocardial Golovic et al. 2020 chronic heart failure present. Yes, no. PC 1 Sayed Shirabad and Menzies. 2005 software defect present 1/0. Tic tac toe aha. 1991 first player wins positive/negative. Fatal Siebert. 1987 car acceptability rating 4 classes. Bank fraud based G set L. 2022 fraudulent applicant. Yes/no. Travel Friday. 2022 hotel booking BS link click. Bank marketing Moro et al. 2011 subscribe to term deposit. Yes/no. Regression bike Fanny T. 2023 total rental bike count. Crab Sidu. 2021 crowd age estimation. Housing pace and vary. 1997 house price estimation. Insurance Aaron Jenger 445. 2023 individual medical cost. Forest 5 Cortez and Moraes. 2007 Burn Forest area Portugal. Wine quality Cortez et al. 2009 wine quality score 010. Cybersecurity attacks ever in venue. Google 2024 alert severity level. Table S2. Tests used to evaluate FAMOSE. Age the age of an individual. Work as a general term to represent the employment status of an individual. FNLWGT the number of units in the target population that the responding unit represents. Education the highest level of education achieved by an individual. Educational number the highest level of education achieved in numerical form. Marital status of an individual. Occupation the general type of occupation of an individual. Relationship with this individual is relative to others. Race gender capital gain last year. Capital loss last year. Hours per week the hours an individual has reported to work per week. Native country of origin for an individual. Table S3. Example feature descriptions for Theta test. 17. FAMOSE, a ReAct approach to automated feature discovery. Age in years. Job type of job categorical. Admin, unknown, unemployed, management, housemaid, entrepreneur, student, blue collar, self-employed, retired, study, science services, marital status categorical. Married, divorced, single. Note, divorce means divorced for widowed. Education categorical. Unknown, secondary, primary, tertiary. Default has credit and default. Binary, yes, no. Balance average yearly balance in euros numeric. Housing is housing loan. Binary, yes, no. Loan has personal loan. Binary, yes, no. Contact communication type categorical. Unknown, telephone, cellular. Day last contact, day of the month numeric. Month last contact, month of year categorical. Jan, Feb, Bar, Nov, Dic. Duration last contact duration in seconds numeric. Campaign number of contacts performed during this campaign and for this client numeric includes last contact. Days number of days that passed by after the client was last contacted from a previous campaign numeric. -1 means client was not previously contacted. Previous number of contacts performed before this campaign and for this client numeric. Outcome of the previous marketing campaign category. Help, unknown, other, failure of success. Table S4. Example feature descriptions for Thetic marketing test. Baseline FAMOSE slot, FAMOSE deep seek. Adult 0.929 plus or minus 0.2 plus or minus 0.929 plus or minus 0.2. Bounce scale 0.914 plus or minus 0.011.0 plus or minus 0.0 plus or minus 0.0. Bank fraud base 0.886 plus or minus 0.040 0.886 plus or minus 0.030 0.885 plus or minus 0.004. Bank marketing 0.934 plus or minus 0.005 0.928 plus or minus 0.013 0.933 plus or minus 0.004. Blood 0.698 plus or minus 0.03 0.704 plus or minus 0.027 0.687 plus or minus 0.009. Breast W 0.989 plus or minus 0.7 0.989 plus or minus 0.986 plus or minus 0.8. Card 0.999 plus or minus 0.0.97 plus or minus 0.003 0.999 plus or minus 0.002. Community 0.866 plus or minus 0.861 plus or minus 0.864 plus or minus 0.5. Call factor 0.99 plus or minus 0.989 plus or minus 0.1 plus or minus 0.1. CMC 0.704 plus or minus 0.019 0.696 plus or minus 0.023 0.698 plus or minus 0.026. Prodigy 0.771 plus or minus 0.036 0.757 plus or minus 0.04 0.748 plus or minus 0.022. Diabetes 0.705 plus or minus 0.004 0.705 plus or minus 0.003 0.705 plus or minus 0.003. Eucalyptus 0.835 plus or minus 0.01 0.836 plus or minus 0.021 0.835 plus or minus 0.03. Hard 0.919 plus or minus 0.023 0.903 plus or minus 0.027 0.916 plus or minus 0.021. Jumbo chest 0.974 plus or minus 0.001 0.994 plus or minus 0.006 0.997 plus or minus 0.001. Daisy 1 0.822 plus or minus 0.05 0.832 plus or minus 0.064 0.832 plus or minus 0.068. Microdol 0.688 plus or minus 0.082 0.679 plus or minus 0.05 0.676 plus or minus 0.09. Take after 0.999 plus or minus 0.21 plus or minus 0.997 plus or minus 0.4. Diddle 0.929 plus or minus 0.007 0.918 plus or minus 0.021 0.93 plus or minus 0.009%. Improvement up 0.0% 0.32% 0.29%. Table S5. FAMOSE specify performance ROC for Claude and DT. We notice that the algorithm works well for both closed source Claude 3.5 Sonnet v2 and open source DTCar1 LLMs. 18. FAMOSE, a ReAct approach to automated feature discovery. 5, 0, 5, 10, 15, 20, 25. Number of functions within code and point me, and point 2, and point 4, and point 6, and point 8, and point 1, and me, and point 1, 2, and 3. FAMOSE figure S1. Number of functions used in COF and FAMOSE code across all task folds 5 times number of tasks. Baseline FAMOSE Sonnet 3.5 v2 FAMOSE DT. Like 40.3 plus or minus 1.03, 40.05 plus or minus 0.99, 39.79 plus or minus 0.73. Crep 2.32 plus or minus 0.132.34 plus or minus 0.082.31 plus or minus 0.16. Housing 409.58 plus or minus 10.54, 408.56 plus or minus 26.34, 396.44 plus or minus 19.22. Insurance 192.89 plus or minus 13.91, 191.64 plus or minus 11.16, 190.16 plus or minus 11.96. Forest size 92.7 plus or minus 5.34, 79.49 plus or minus 5.87, 79.47 plus or minus 4.6. Wine quality 0.64 plus or minus 0.02, 0.64 plus or minus 0.01, 0.64 plus or minus 0.02. Cybersecurity attacks 0.82 plus or minus 0.82 plus or minus 0.82 plus or minus 0.0. Percent reduction up area 0.0%, 2.0%, 2.8%. Table S6. FAMOSE regression performance RMSE for Claude and DT. Bold are best performing models. We notice that the algorithm works well for both closed source Claude 3.5 Sonnet v2 and open source DTCar1 LLMs with a slight edge for DTCar1. 19. FAMOSE, a ReAct approach to automated feature discovery. df.drop add mult divec bit and sub gt dfdbh.step in functions 0.02.55.07.51 0.01 2.51 5.0 of functions across datasets. Figure S2. Frequency each function used in COF code across all task folds 5 times number of tasks. Auto B1 random forest. Baseline FAMOSE adult 0.929 plus or minus 0.003 0.929 plus or minus 0.002 0.903 plus or minus 0.002 0.901 plus or minus 0.005. Bounce scale 0.995 plus or minus 0.004 1.0 plus or minus 0.0 0.806 plus or minus 0.091 1.0 plus or minus 0.0 0. Bank marketing 0.93 8 plus or minus 0.004 0.93 7 plus or minus 0.006 0.929 plus or minus 0.004 0.928 plus or minus 0.003. Bank fraud base 0.877 plus or minus 0.01 0.884 plus or minus 0.006 0.834 plus or minus 0.003 0.835 plus or minus 0.004. Blood 0.757 plus or minus 0.035 0.747 plus or minus 0.029 0.686 plus or minus 0.042 0.706 plus or minus 0.03. Breast W 0.993 plus or minus 0.005 0.994 plus or minus 0.005 0.991 plus or minus 0.006 0.992 plus or minus 0.006. Core 1.0 plus or minus 0.00998 plus or minus 0.004 0.994 plus or minus 0.002 0.992 plus or minus 0.003. Community 0.866 plus or minus 0.862 plus or minus 0.869 plus or minus 0.7 plus or minus 0.0. CMC 0.726 plus or minus 0.014 0.708 plus or minus 0.019 0.698 plus or minus 0.014 0.688 plus or minus 0.024. Cotype 0.998 plus or minus 0.00998 plus or minus 0.00997 plus or minus 0.00997 plus or minus 0.001. Heredity 0.75 plus or minus 0.042 0.761 plus or minus 0.016 0.791 plus or minus 0.022 0.764 plus or minus 0.026. Diabetes 0.699 plus or minus 0.005 0.7 plus or minus 0.004 0.676 plus or minus 0.002 0.675 plus or minus 0.002. Eucalyptus 0.879 plus or minus 0.028 0.889 plus or minus 0.021 0.886 plus or minus 0.012 0.882 plus or minus 0.015. Heart 0.928 plus or minus 0.023 0.92 plus or minus 0.027 0.927 plus or minus 0.028 0.91 plus or minus 0.037. Gender test 0.998 plus or minus 0.011.0 plus or minus 0.0.932 plus or minus 0.010 0.996 plus or minus 0.002. Myocardial 0.69 plus or minus 0.075 0.699 plus or minus 0.051 0.709 plus or minus 0.087 0.676 plus or minus 0.041. PC1 0.824 plus or minus 0.067 0.82 plus or minus 0.079 0.84 plus or minus 0.044 0.855 plus or minus 0.053. Tic Tac 0.999 plus or minus 0.001 0.999 plus or minus 0.002 0.998 plus or minus 0.004 0.999 plus or minus 0.002. Legal 0.938 plus or minus 0.014 0.933 plus or minus 0.021 0.93 plus or minus 0.009 0.923 plus or minus 0.019. Percent improvement up 0.0%, 0.02%, 0.0%, 1.2%. Table S7. Robustness of classified performance ROCUC for FAMOSE XG boost features applied to different models. Random forest and audibly one bold indicates the best model. 20. FAMOSE, a ReAct approach to automated feature discovery. Add multi subdivic apps and t.log1 pmp.sqrt bit and functions 0.02.55.07.51 0.012.515.01 7.5% of functions across datasets. Figure S3. Frequency each function used in FAMOSE code across all test folds 5 times number of tests. Audibly one random forest. Baseline FAMOSE like 35.37 plus or minus 0.92 35.41 plus or minus 0.96 42.02 plus or minus 1.53 41.97 plus or minus 1.23 grab 2.13 plus or minus 0.11 2.1 plus or minus 0.13 2.19 plus or minus 0.09 2.18 plus or minus 0.09 Housing 384.31 plus or minus 15.11 300 E1.08 plus or minus 18.47 418.38 plus or minus 11.23 416.28 plus or minus 14.05 Insurance 166.59 plus or minus 13.31 174.56 plus or minus 16.7 178.82 plus or minus 8.87 183.44 plus or minus 11.0 Forest fires 80.89 plus or minus 6.11 79.16 plus or minus 5.59 83.13 plus or minus 5.04 79.22 plus or minus 5.68 White quality 0.61 plus or minus 0.01 0.61 plus or minus 0.01 0.61 plus or minus 0.01 0.61 plus or minus 0.02 Cybersecurity attack 0.82 plus or minus 0.82 plus or minus 0.83 plus or minus 0.82 plus or minus 0.0 percent reduction up 0.0% 0.1% 0.0% 0.5%. Table S8. Robustness of classified performance RMSE for FAMOSE XG boost features applied to different models. Random forest and audibly one bold indicates the best model. 21. FAMOSE, a ReAct approach to automated feature discovery. Call FAMOSE 0.2, 0.4, 0.6, 0.8, 1.0% folds with featured engineering. Figure S4. Percentage of test folds 5 times number of tests where FAMOSE or call features were added. No goal in prompt, only feature selection, no feature selection. Like 40.19 plus or minus 0.89, 40.3 plus or minus 1.03, 40.43 plus or minus 1.54, grab 2.34 plus or minus 0.14, 2.34 plus or minus 0.12, 2.34 plus or minus 0.09. Cybersecurity attack 0.82 plus or minus 0.82 plus or minus 0.83 plus or minus 0.0. Forest fire 79.87 plus or minus 4.98, 79.54 plus or minus 5.89, 92.93 plus or minus 5.24. Housing 409.03 plus or minus 26.18, 409.58 plus or minus 10.54, 418.51 plus or minus 38.84. Insurance 186.53 plus or minus 12.52, 184.43 plus or minus 16.86, 193.95 plus or minus 13.82. Wine quality 0.64 plus or minus 0.01, 0.64 plus or minus 0.01, 0.64 plus or minus 0.01. Percent reduction up arrow 2.2%, 2.4%, 0.8%. Table S9. Ablation for regression tests. We see a slight improvement in the RMSE reduction when we only select features. Although the difference is not significant, Wilcoxon signed rank test p-value equals 0.3. But the difference between FAMOSE and no feature selection is significant. Wilcoxon signed rank test p-value equals 0.7. Overall, our results show FAMOSE performs best when we have a goal in feature selection. 22. FAMOSE, a ReAct approach to automated feature discovery. No goal in prompt, only feature selection, no feature selection. Adult AI.928 plus or minus AI.2 plus or minus AI.929 plus or minus AI.2. Bound scale 1.0 plus or minus 2.914 plus or minus 2.0 1.0 plus or minus 2.0. Bank fraud basic 2.885 plus or minus 2.3 0.885 plus or minus 2.5 2.881 plus or minus 2.01. Bank marketing 0.928 plus or minus 2.5 0.933 plus or minus 0.2 0.929 plus or minus 2.011. Blood 0.678 plus or minus 0.038 0.688 plus or minus 0.024 0.679 plus or minus 0.024. Breast W 0.99 plus or minus 0.080 0.989 plus or minus 0.985 plus or minus 0.011. Car 0.999 plus or minus 0.097 plus or minus 0.02 0.998 plus or minus 0.002. CMC 0.691 plus or minus 0.01 0.704 plus or minus 0.023 0.7 plus or minus 0.015. Community 0.859 plus or minus 0.05 0.861 plus or minus 0.7 0.866 plus or minus 0.7. Cough 0.992 plus or minus 0.989 plus or minus 0.989 plus or minus 0.02. Credit 0.755 plus or minus 0.021 0.756 plus or minus 0.036 0.758 plus or minus 0.04. Diabetes 0.705 plus or minus 0.04 0.705 plus or minus 0.03 0.76 plus or minus 0.04. Eucalyptus 0.831 plus or minus 0.024 0.836 plus or minus 0.027 0.825 plus or minus 0.023. Hard 0.913 plus or minus 0.02 0.916 plus or minus 0.019 0.914 plus or minus 0.023. Jungle Chest 0.999 plus or minus 0.010 0.974 plus or minus 0.010 0.994 plus or minus 0.06. Mycardo 0.664 plus or minus 0.077 0.663 plus or minus 0.067 0.677 plus or minus 0.076. PC1 0.826 plus or minus 0.067 0.825 plus or minus 0.056 0.82 plus or minus 0.054. Detector 0.996 plus or minus 0.61 plus or minus 0.998 plus or minus 0.3. Beagle 0.929 plus or minus 0.004 0.921 plus or minus 0.01 0.924 plus or minus 0.07% improvement up 0.0% 0.38% 0.04%. Table S10 dot ablation for classified tests. Due to the small changes in ROCAUZ, the results are not statistically significant, except for only feature selection, which is significantly worse than the baseline and FAMOSE Wilcoxon signed rank test p-value 0.04, which suggests that we need to go beyond feature selection alone to achieve high performance. Overall, our results show FAMOSE performs best when we have a goal in feature selection. 23.